Okay, time to get started. So, new section today. This is another one of these monster sections. This is going to take us several days to get through, at least three, probably. Anyway, so here we go. We've developed a lot of tools, and what we're about to do is apply them to a new circumstance, but following the exact same pattern that we've already applied in several other circumstances. So this is going to go a little bit more quickly than we've done in the past. In particular, we're going to start talking about Gauss's divergence theorem. And let's see here. Quick note: the book starts with Stokes' theorem. It's an unusual choice, not right or wrong, right? It's not my preference. I like to start with the divergence theorem, Gauss's divergence theorem, sometimes called the divergence theorem, sometimes called Gauss's theorem. Find it a little bit easier to digest and a good sort of better segue. But anyway, all right, so off we go. So just like with Green's theorem, we need to talk about what do we mean by boundary. And good news, it's not a crazy notion. Here is a three-dimensional region, for example. Now you'll notice I've deliberately made a weird three-dimensional region that kind of has an air bubble in the middle of it. That's on purpose, so that we can talk about how to treat that. There is our solid region R. And now, what is the boundary surface? That is the boundary of R. Right? The boundary. Again, we use the little partial derivative symbol to represent boundary. It's just notation. It's a little weird notation, but it's just notation. That's exactly what you think it is. It's sort of the border between where the solid is and where the solid isn't. And of course, there's this, what you might call the outside part of the boundary, but then of course there's also the inside part of the boundary. And again, there's a little air bubble in there. And this too is the border between where the set is and where the set isn't. So the subtle part is, again, boundary. It needs to be an oriented notion. Boundary in this case being a surface. We need to talk about some appropriate choice of orientation on a surface. So we have to talk about some appropriate choice of a direction of the two possible directions through the surface. Which one do we pick? And the answer is, again, commonly misstated as outward. It's not really quite true. The point is, away from where the solid is and into where the solid isn't. Right now, again, it looks outward. And for the outer part of the boundary, it is outward. But notice for the inner part of the boundary, it's not outward, right? This is inward, really. I mean, like if you were to imagine this having an inside, a lot of people would call this inward. So again, be careful with the sort of the sloppy rephrase, the convenient little shorthand of calling it outward. It's not quite that simple. Does everybody see the distinction? Everybody clear on the convention here? Again, arbitrary but standard, not optional. Okay, and with that established, I'm going to observe that, I'm going to give myself some more space too. I'm going to observe that boundary flux is an accumulating quantity. And I'm going to make the statement that, we've already kind of seen this in some sense. Right? Let's go back to chapter 6, I guess it was. We already talked about how boundary flux accumulates. Right? We just talked about how boundary flux accumulates in a two-dimensional context. Right? So we drew this picture, right? And we're boundaries being boundaries of a two-dimensional region, those boundaries therefore being curves and all of that. So this picture and, interior edge appears twice, opposite orientations, and it cancels. And, well, here we are again. Now it's a three-dimensional solid with a two-dimensional boundary surface. Yeah. But I mean, still, look, there's this interior now face, right? And it appears twice as parts of the boundaries of these left piece and the right piece. with opposite orientations, and they cancel. So it's really the same idea. Does everybody see how this is just a kind of a rehash? This is a borrowing. This is a sort of a, just a total rip-off of what we did in 2 dimensions. Any questions about that? Okay. So we have ourselves an accumulating quantity, and once you have something that's accumulating, then you can we'll go through the usual song and dance, right? So I'm going to encourage you to think of this as being a kind of a substance, kind of a physical stuff. It's not, right? But it is extremely handy to think of it as being a kind of a substance, sort of a concrete physical stuff. And, if you say, well, how much of this stuff is there in this region? Well, compute that flux. Compute it on the boundary, of course. Flux is defined on the boundary, but that will tell you how much of this substance, what I'm claiming is this substance, there is on the interior. And then if you further say, okay, well, how much of that substance, how much of it is in that little region of the interior? Oh, no problem. How much is in that region? Well, you would just compute the flux on that region. That tells you how much of the flux distributed over the interior is actually sitting inside there. Right? Now, it doesn't have to be physically true for this to be useful. The fact that this is flux, boundary flux, oriented according to the convention, the fact that it's an accumulating quantity means this fictitious, made-up sort of point of view will always add up correctly. So it behaves like a stuff, so you might as well think of it as a stuff because, again, it's very, very sort of intuitively handy and geometrically handy and big win. So I'm a big fan and I strongly encourage you to think of it as a stuff. And then, next step, and again, we've done this several times previously, once you have a stuff, you can talk about how much stuff per unit volume. Right now, I'm drawing this as a 2-dimensional picture just because it's hard to draw 3-dimensional pictures, especially when I need to talk about the interior and the boundary surface, and they kind of overlap. It's just a harder picture to draw. So you can use your imagination. But per unit volume, right, we can ask how much flux, how much of this stuff called flux, which of course we measure and compute on the boundary, yeah. But how much of that flux stuff is there distributed throughout that interior volume? And we get a notion of density. This notion of density, total ripoff of our notion of mass density. Again, no surprise. This, when the quantity in question is flux, we call it flux density. Right? And we've talked about that term previously. Again, extremely natural and very common. Very common. Again, in my physics classes way back when, I heard the term flux density more than I heard the sort of the math alternative, you might call it, which is divergence. So I really like this term flux density. I wouldn't say that I'm going to use it exclusively. I'm certainly not, but I like it better, right? Just on a sort of a personal level. The operator is called divergence, but I encourage you to think of it as flux density. Let me say it that way. How we doing so far? Things all right? Okay. So here's the formula for it. You probably recognize, we saw that back in chapter 3. And back in chapter 3, I made this apologetic, trust me for the moment. We'll have a context for this later, but I claimed that it says, all right, well, in some sense, how much is the fluid kind of flowing outward away from wherever you compute it? I gave you no reason other than your possible faith in me in the book to believe it. So now we have a kind of a reason to believe it. Now, I'm not going to show you the actual calculation that comes to this specific formula, but the fact that divergence represents sort of an outward flow, you can kind of see now, because flux is literally a measurement of the flow rate of the fluid through the boundary in the outward direction per the convention. So it is literally the outward flow of fluid, with the understanding, of course, that, if you're going to talk about the outward flow of fluid, you have to have a surface. If you have a closed surface, there has to be an inside. We can't talk about this at a single point, so we talk about per unit volume and take a limit as these pieces get small. Right? But it remains that what fundamentally we're talking about computing is this outward-oriented boundary flux, which is literally to what extent the fluid's flowing out. Okay, everybody okay with that? This is a resolution of a dangling thread that we left from chapter 3. Okay, shorthand notation, div F. You'll see that sometimes. More common shorthand notation, del dot F. We talked about that back in chapter 3, so that's just a quick reminder. Also, very, very common. You'll see del dot a lot. Okay, everybody happy? Everybody on board? By the way, just for your consideration, when I wrote these notes, I very deliberately sort of followed the same sort of pattern of talking about boundaries first and then noting an accumulation quantity and then talking about the stuff perspective and then talking about density, etc., just like we did back in Green's theorem. Again, on purpose, because I want you all to see how these are structurally extremely similar theorems. They're motivated by very analogous arguments. So I think it'd be a healthy exercise to go back into the section on Green's theorem and kind of look how we developed that, look how we developed this, and note the analogies and see the comparison. And a lot of potential benefit there. Okay, now this is, I'm going to wave my hands at this. It is, y'all can read this, it's just a computation. But keep in mind, if we have a certain amount of flux, some vector field through some surface, right? Well, if I claim that stuff, that is a kind of a stuff, and that it's distributed across the interior, I could reasonably ask, well, is there kind of, in some sense, is there more of it at the point A, or is there more of it at the point B? Where would I find more of this stuff? Or said differently, flux being an outward flow of fluid, where's that fluid sort of coming from? Is it more so coming from the point A, or is it more so coming from the point B? And, well, if you want to know where the flux mostly comes from, you look at flux density. Flux density tells you where the flux is. Or if you want to, again, interpret it as flow of a fluid, it tells you where the flow is coming from. And so you just take those points, you plug in, you get the two different values, you see that this is the bigger value, and so therefore B, there's more flux coming from the point B than the point A, because the divergence tells us so. Okay, so anyway, just I wanted to real quick talk about that. Make sure to read these details. By the way, another suggestion. Look at this example and then flip back real quick to where, let's see, in 6.2, I think it was, in Green's theorem, I made an analogous couple of examples concerning two-dimensional divergence, two-dimensional curl, and all of it sort of by comparison to the fundamental theorem of calculus. Right? Where the derivative tells you where change is happening. Right? That's, of course, derivatives tell you where change is happening in some sense. And in the same sense, divergence tells you where flux is happening. Yeah.
So just to confirm, the stuff is moving away from the point.
Yeah, that's right. Yeah. So when we say boundary flux, the convention on boundaries, they're oriented outward, and so the flux, positive flux means outward flux. Yeah. Okay, so let's write down the theorem. We already have all the ideas. We've talked about the idea of thinking of flux. Let me say that differently. Boundary flux as a quantity defined on a region. If you give me some region, three-dimensional region, I can talk about the boundary of that region. I can then say what's the flux of your vector field through that boundary of that region. We have here a quantity defined on three-dimensional regions. We've made the case that it's an accumulating quantity. Right? Holds the sum of the parts, that's all that says. And as any accumulating quantity has a corresponding notion of density. Oh, I can't use green. I already used green. Color choices. I'll use dark green. Any sort of stuff has an associated density. Divergence, of course, is that density. And bam, we've got ourselves a theorem. And this is called Gauss's divergence theorem. Or, again, Gauss's theorem, the divergence theorem goes by several different names. How we doing? Does that make sense to everybody? Is everybody kind of playing along, following along? Everybody's happy? Okay, now there are certain conditions. We do need the vector field to be nice, and I don't want to get into the weeds on the region has to be a plausible region. Anyway, good news, any region you can dream up probably is fine, right? But anyway, there are formalities that I want to, for the record, I am ignoring for the purposes of this course. I will note that this only works when there's no singularities. Right? If the vector field fails to be defined, even so much as at a single point, crash and burn. Real problems come up. And we'll talk in a few minutes about, an example of such a crash and burn and how we can kind of recover some value out of this in such cases. But in general, very important, no singularities. Okay. All right, let's see an example. I mean, again, we're going through this quickly because we've been down this road several times. And okay, so here you go. Here's a question. By the way, as I've commented on several analogous examples that we've seen in the past, note that this question does not announce itself as by the way, this is a Gauss's divergence theorem question, or hint, use Gauss's divergence theorem. Right? There is no indication of how you're supposed to do this. The question just says, here's a surface, here's a vector field, compute the flux. We know several ways to compute flux. Right? So, we're going to have to decide what the best way to compute this flux is. And now, you could brute force this, I suppose. Right? We're talking about the unit sphere. We can parameterize the unit sphere. We're going to have to choose between square roots or trig. And again, I'm always going to pick trig. And you give me that choice, square roots versus trig, I'm always going with trig. Right? But then you think to yourself, well, if x, y, and z are chock full of trig, then this vector field is going to turn into a nightmare. And so let's not do it that way. I think that'd be really hard. So our alternative is to try to use the divergence theorem. Whoa, here it is. Do notice that there is a big asterisk. If you want to compute a flux, and you're like, hey, how about why not use the divergence theorem? Why not just do a triple integral of divergence? Very important asterisk. Only for boundaries. Really big deal. By the way, I see so many students, that happens so much. Less, as I make a big dramatic deal out of it. Okay? Thus the drama, thus the emphasis. But I certainly used to see lots and lots of cases of students computing a flux, trying to compute a flux to a surface that isn't a boundary by writing down some corresponding triple integral in it. Makes no sense at all. There is no such theorem. The Gauss's divergence theorem is only for boundaries. right? So really careful about that. This only works for boundaries. By the way, for whatever it's worth, aside from, rigor and all that, it has to be a boundary because it has to be a boundary of a solid, because that would be the solid for my triple integral. So for your consideration, if the flux that you're interested in is not the boundary of something, if there is no R, not only is the flux not equal to this triple integral, there is no triple integral. Because there is no region on which to even talk about it. Does everybody see so this is why I say this is a catastrophic mistake. Please, oh my gosh, please be careful about this. Don't make the mistake of just taking some arbitrary flux that's not through a boundary and then start talking triple integrals. It makes no sense at all. Okay. All right. So we've got to look back at our example here and ask, is our surface a boundary? Well, unit sphere, and it's tempting to say that that's a boundary, but the problem is it says also right here, inward oriented unit sphere, which means our actual surface is like that, and that is not a boundary. Per the convention about orientations, right? Orientations have to be, away from where the solid is, into where the solid isn't. This isn't it. So, not a boundary. Shoot. Okay, well, all right, but here's the good news. That surface, I'm just going to leave half of it highlighted, very closely connected to this surface. Same surface, just oriented outward. All right, notice that minus sign there. That is a boundary. So all I have to do is recognize that the flux that I want, that's the flux that I was asked for. That flux that I want is just the negative of the flux through S minus, which of course is a boundary flux. Now let's take a pause, make sure everybody's happy with this. Is that cool? Everybody good with that? And don't forget that minus sign, of course, continues. And here's where we can use the divergence theorem. We literally have a boundary flux. The divergence theorem says a boundary flux is a triple integral of divergence. Again, don't forget to continue those minus signs. And Gauss's divergence theorem has now rephrased our question into a totally different question. Okay, now how to deal with this integral. What are we going to do about this integral? Let me go ahead and... okay, whatever. How to compute this integral. Well, it's a triple integral. Those can be tedious. The domain's a unit ball. My first thought is spherical coordinates. Right? When your domain is a ball centered at the origin, spherical coordinates is set up really nicely for that. That's a reasonable choice. You can, in fact, work it out that way. That would be fine. But look at the following super clever alternative, and that is to break it up as two separate integrals, right? And here's the good news. That's the integral of a constant over a barnyard variety geometric figure. That integral's obvious, right? And this is zero by symmetry. So be on the lookout for this move. This is a real trouble saver. Yeah.
What line is the zero? Is the x?
Oh, let's think that through. Okay, so we need the integrand to have odd symmetry. Odd symmetry would come from whatever my reflection is needs to turn x into the negative of x. And if you think about it, reflecting through the YZ plane will do exactly that. Yeah, so this is zero by symmetry through the YZ plane. Does that make sense?
Yes.
Everybody happy with that? Yeah, and I guess to satisfy my own rules, if this had been on an exam, I would have to indicate through what plane, right? So do make sure to follow that rule. Okay, so turns out this integral happens to be super easy to compute, and there you go, and we win. Way better than doing this by brute force. Everybody all right? Okay. So let's talk about some physical examples. These are really interesting exercises. There's going to be a lot to visualize here. We will work our way up to actually making some really powerful conclusions about physics. This first one's not so much, but we are eventually going to work our way up to, I think, learning big, powerful, sophisticated points of view on how gravity works, how electromagnetism works. A lot of tremendous value on its way. So let's start with this example, though. It's a good starter example. It's just a light bulb. And a light bulb, of course, these days anyway, has a little LED at the middle, right, at the center. And I could say, well, let's imagine that this is this surf. Let's do this in green, I guess. This surface here is, let's call it the case. The glass or plastic part that protects the LED from bugs getting in there and stuff, right? So, all right, let's talk about how much light this is putting out. And, well, the LED is generating a certain amount of light. And, by the way, we can write a formula for that vector field. This flow of photons like so. Now, I've written that small. Talk about y in a second. But you might recall kr over magnitude of r cubed. That's the inverse square radial vector field. So we talked about this back in chapter 3. Here's the problem when I say that this is the vector field. Couple of questions come to mind. One is, hey, wait a minute. Light bulbs emit photons. Don't all photons go at the same speed? Why is this vector field doesn't have constant magnitude? Right? And the reason why is because this is not representing velocity. This is representing velocity times density. Right? So this vector field is set up to talk about the actual flow of quantity per unit time is something that we're going to be interested in talking about. And remember, if you're interested in quantity, not volume per unit time, you got to factor in the density, and that's what makes this not have a constant magnitude. Is that cool? Everybody okay with that? Seem reasonable? Okay. And of course, as the photons move farther away from the LED, they necessarily kind of spread out, and so the density goes down. All right. Here's the other asterisk. We need to talk about this. This is only valid away from where the LED is if you're actually where the LED actually is on the LED, like inside the LED. All bets are off. I don't know, but this is certainly not correct on the LED itself. All right, so this is only, I'm going to say off of and away from the LED. Okay, so a couple of observations to make about this fluid flow. Let me go ahead and clean up the mess. This is a steady state deal. Okay. You flip the light on, photons start flowing, and it's not. I mean, if I were to put some sort of a region over here, transparent region, and say how many photons are in that region at any given point in time, it's not changing. We're not collecting photons. Photons just whiz right on through. right? And then more photons whiz right on through right after them, and we're not collecting more and more photons, or we're not depleting space's supply of photons in any given region. So it's a steady state deal, and the density does not change. Does that make sense to everybody? Okay, now I'm going to remind you, this is back to chapter 3 now. We talked about a different vector. This is not the same vector field. Different vector field. There's the formula. Very different vector field. But we computed the divergence, and we observed that this is, okay, well, there, you can see there's an outward flow. The divergence ended up being positive, and I said, well, it's at least consistent with the claim, and we didn't prove anything, but this was just a kind of a see what I'm talking about kind of example. And then we made a consideration of, what does this mean physically? What is that representing physically? And I pointed out that there's a couple of different possibilities of how you can think about fluid flows. You might think about fluid flows as, well, there's a certain amount of stuff, and that stuff is going away, and so you are losing stuff, and therefore the density would be decreasing. Or you might, such as in our light bulb example, you might say, well, maybe the fluid's just being created. And yeah, it's flying away, but it's being constantly generated, and therefore the density is not changing at all. Right, so it depends on the kind of fluid you're talking about. So I made the comment at the time that you got to think about your physical scenario and try to make sense. Wait a minute, which one of these cases is it? What kind of a fluid are we talking about before you can actually interpret how, make a reasonable case for how to physically interpret divergence. Right? So in this case that we have here, we are talking about the version of those two choices where we're generating the fluid and the density is constant. Is that cool? All right. Okay, so let's talk about divergence. I'm going to start by making the claim that the divergence is zero pretty much everywhere except where the LED is. So, for example, in this general area that I've got in green here, I claim the divergence is zero here. And let me give you a really simple argument. I'm not even going to do a calculation. Now, you could, by the way, you can just straight up take the divergence. It's algebra. In fact, I think you may have already done this calculation back in Chapter 3. You may have already computed the divergence of this. Another little side note, just to kind of remind you of something. When you compute the divergence of this, you have two choices. You can write this in rectangular coordinates and use the simple rectangular formula for divergence and deal with all the resulting square roots and fractions and other related nightmares. Or another alternative is leave this in spherical. Right? I've got this represented in spherical coordinates here. And then use the spherical, the harder to write down, right, uglier, scarier looking spherical divergence formula, and much easier calculation. Right? So I strongly encourage if you ever do need to redo that calculation to compute the divergence, oh my gosh, do it in spherical, of course. This would be way better, way nicer calculation. But here's the easier argument, and I think this makes loads of sense. This is a good physical sort of metaphor that y'all can think through, and when you get into physics classes where they're talking about inverse square radial vector fields like electricity and gravity and stuff like that, note we have an inverse square radial vector field here, right? And so structurally, any inverse square radial vector field, they're all kind of the same. So the following argument, while it makes physical sense here, is perfectly reasonable for any inverse square radial vector field. And here's the argument. We want to compute the divergence in that general area. Okay, well, let's look at the boundary. let's compute the flux through that boundary. How would I compute the flux through that boundary? Oh my gosh, am I going to have to parameterize that sphere and do a plug and chug? No, I'm going to compute the flux through that boundary in a snap by arguing, look, the flux, you mean the flux of the photons? You mean the photons that are emanating out of here? You mean those photons that every one of which that goes in just comes right back out? You mean those photons where every inward flux through is paired up with an outward flux through? The flux is zero. All the inward flux perfectly balances all the outward flux because every photon that flies in also flies out. Is that cool? It's a really, you got to think it through, right? You got to make sure you understand the scenario, but in this case, it's a pretty direct and simple argument. So if the flux is zero, and if that applies everywhere, stay away from the LED, right? But if it applies pretty much everywhere, if the flux is always zero, then the flux density is zero. That means that divergence is zero. And that means that I don't need to do this calculation here at all. Does that make sense to everybody? Y'all good? So, nice argument, really valuable argument. Now, so I claim, divergence is zero away from the LED. And now, what's going on at the LED? Well, that's harder to say. We don't have the formula for the vector field. I don't know. I literally don't know what how deeply inside the LED do photons emit from. I'm not sure. Okay. But I don't need to, because I can make the following argument. Let's look at a little region containing the LED. And let's think about the boundary. And let's ask the question, what is the flux through that boundary of this little blue region that contains the LED? So keep in mind, flux, vector surface integral, just means flow rate, right? So the fluid is photons. When I say what's the flux, what I mean is what is the flow rate of photons? How many photons per second are passing through that purple surface? And again, there's a really simple answer to this question. How many photons? All of them. Right? Every photon that's generated by this LED, they all flow out of that surface. Everybody happy with that? All right. Okay, so that's the flux. What's the flux per unit volume? Oh, okay, well, you notice the flux doesn't depend on how big this thing is, right? This blue region could be big or it could be small. I could let it get smaller and smaller and smaller. And keep in mind, those little LEDs are teeny tiny little things. They are quite small. So we're talking about what I'm going to call a substantial amount of flux, right? LEDs put out a lot of lumens, right? Photons per unit time. Lots of lumens. And this volume, very low. So what's the flux per unit volume? What is substantial divided by very small? Well, it's huge. Does that make sense? Okay. So that's why I say where the LED is, the divergence is huge. Okay. Everybody happy so far? Okay. All right. So, nice conclusion. I've made the claim that divergence tells you where the flux is coming from. And, back in, previous contexts, I looked at this picture here and I made the case that, we measure flux on the boundary, but imagine that it's actually distributed throughout the interior. Ooh, right? This weird, kind of hard to buy. Come on, that's basically nonsense. Flux is on the boundary. Come on, look at the formula. That's how we compute flux. It's on the boundary. And this case that I make for it's in the interior. And by the way, divergence tells you where. this is kind of a hard-to-buy, seemingly made-up bunch of nonsense, right? But check it out. Check out what divergence is doing now. I've made the claim that the flux through the bulb, right, we got a certain amount of flux there. Now if I make the claim that, hey, that flux that we measure on the boundary, it's actually coming from the interior, well, of course it is. That's where the LED is. That's where those photons are coming from. And furthermore, divergence explicitly tells us exactly where the divergence is, that flux that we measure on the boundary is actually coming from. And furthermore, it also tells us where it isn't coming from. Right? This flux that we're measuring on the boundary, it's coming from where the divergence is huge, where the LED is. It's not coming from here. There's no flux being created here. There's no photons being generated here. And divergence just gets right up on it. Isn't that cool? I think this is a fabulous starter example. Again, y'all know, I'm a big fan of this idea of thinking of accumulating quantities as distributed over the interior. And again, here we have one where that's pretty believable. In this case, physically believable. Okay. All right. So again, this is something to chew on. This is something you want to spend some time with, digest, and really kind of cozy up to the idea that, oh my gosh, divergence really is telling us where there really is kind of a stuff in the interior, and divergence tells us exactly where it is. Okay. So let's talk about a singularity. So the limiting case of the above, right? So let's go back up to here, and you notice I wrote this in small print, inverse square radial, but away from where the LED actually is. The actual LED has a tiny, small but finite amount of size, and there in this non-zero sized region, I have to kind of throw up my hands and say, I don't know, right? Okay, so in the limit, if you let those LEDs, I mean, imagine a technology allows us to make LEDs smaller and smaller and smaller, right? In the limit, and we're talking about this actual vector field, right? This vector field is defined everywhere except for the origin. The origin is the only point where this is not defined. So can I use this as a sort of an approximation of the physical scenario we were looking at above? And if so, how does that change things? And does the theorem still work? We do have a singularity. The condition we put on the theorem is that we can't have any singularities. So kind of what goes wrong and what can we salvage is kind of what I want to talk about here. Okay, well, divergence is still zero everywhere else. Right? Everywhere except the origin. And of course, at the origin, there's no such thing as divergence. The vector field isn't even defined there. Okay, all right. Well, let's look at the theorem. Here's the divergence theorem. If it were going to work, I would need these two integrals to equal to each other, and let's just kind of see if it makes sense. And all right, well, let's start with a triple integral of divergence. Well, if the divergence is zero everywhere, except for one geometric point, right? Doesn't even have any volume. What's that triple integral? Well, in fact, the triple integral isn't technically defined either, and okay, we can't actually quite answer the question of what that triple integral is. It's just not defined. But if you were going to give it a value, we're doing a triple integral of something that's zero everywhere, except for possibly a single point. I mean, one single point, I think we would probably, if we were going to give an answer to this, we'd probably say the answer is zero. Does that seem like a reasonable take? But again, I don't want to get into the weeds of formalities. Okay, well, that would kind of suggest then that boundary flux perhaps that should also be 0? Is the boundary flux 0? And, well, no, it's really not. The boundary flux, for example, if you talk about a region that surrounds the origin, like that, the boundary flux is not 0. Boundary flux is 4 pi k, where k is that constant in the original formula for the vector field. K basically is proportional to how bright of a light bulb is this. Right? Bigger values of K means you got more lumens on your light bulb. So, oh yeah, question, yeah.
Where did the 4 pi come from?
Oh yeah, right. So I haven't justified this, right? So I'm not going to give you a complete argument for justifying this claim, but I am going to make a suggested exercise. The way you can kind of make yourself believe this is do this calculation for any sphere centered at the origin. And it's a very straightforward calculation. If you pick a sphere centered at the origin, then all your normal vectors are parallel to your field vectors, and the calculation just kind of falls apart pretty straightforward. And ultimately the 4 pi comes from the fact that that's the area of the unit sphere. But that is a good exercise, and I want to encourage everybody to take a crack at that. Let this S here be, let's say, importantly, any sphere centered at the origin. And just crank out this calculation, and you'll get 4 pi k. As always, come talk to me in office hours if you get stuck, have any questions, not sure how to get started, whatever. Okay, so, problem. Does the theorem work? Well, not really. One side isn't defined. I'll give you 2 seconds. One side isn't defined. If anything, that side that isn't defined, we'd want to call it 0. And the other side, unambiguously, at least in some cases, definitely not 0. So I'm going to say the theorem has in fact crashed and burned. And the question we're going to move on to right after your question is, can we recover any value out of this? Yes.
When you say if f surrounds 0,
yeah.
Do you mean that it's based, like the center's at the origin?
No, I'm saying any surface, such as what I have labeled over here, called S1. This surface, as long as it tracks the origin inside of it,
okay,
then that integral will be 4 pi k. And I don't suggest that you try to prove that specifically, because that requires a little bit of careful setup. But try the concentric spheres example, and for those specific surfaces, it's a pretty straightforward calculation. Okay, so here's the argument. So we gotta jettison the theorem, but the theorem, keep in mind, it's just we have a point of view on the theorem, which is that there's this stuff, and the flux is just a measure of how much stuff there is on the inside. Normally we compute how much stuff there is by integrating the density of the stuff. The only thing we have to do to fix this is to just acknowledge that in this case we have the stuff that's not distributed over volume. Here we have a discrete lump of stuff right there at the origin, a point lump in the amount of 4 pi k. That's how much of that lump of flux there is at the origin. And now everything kind of works fine. Let's talk about S1. For S1, if I want to talk about the flux through S1, and if I want to claim that the flux through S1 is a measure of how much stuff there is on the inside, well, there's no stuff. Divergence is 0. No stuff over here, and then there's a lump of stuff in the amount of 4 pi k. Grand total, how much stuff is in S1? 4 pi k. Just as the calculation says. Okay, now let's talk about this surface S2. All right, let's talk about what is the flux through S2. Well, let's see here. Flux through S2. Flux through S2 is, I need to look at how much stuff there is on the inside. How much stuff is there? Well, divergence is 0. There's no stuff anywhere Well, anywhere inside of S2. There's a lump of stuff outside of S2, but that's not the interior. That's not part of the region that S2 is the boundary of. So there is no stuff inside of S2. So we think that flux should be 0. And again, it is. So this is the fix. All you got to do is just kind of edit your point of view on how we think about flux as a stuff. It doesn't have to be exclusively distributed over volume by density. It can come in little single point unit lumps. And by the way, doesn't that sound familiar? We talked about a very similar point concerning Green's theorem and circulation back in 6.2. Okay, good place to end it. Y'all have a good rest of your day. See you later.
Thank you. Have a good one.
Yeah, you too.